time slice expiry or so, this may get from running to the ready state. Then all the process will again follow suit. That is, it will again be again be dispatched to the running state. It might come back to the waiting state for this IO devices or this one. Do remember, only when the process is in this state, that is in the running state, the process is executing. All the other states, this state, or maybe in this state, the process is doing what? Process is waiting. Am I being clear now? Yes or no?
Yes, sir.
Sir,
Yes, sir.
Yes, Arunab,
sir, what if the RAM gets filled?
I'm coming to that. I'm coming to that. As of now, you consider that a process is created. Okay, a process is created. A process will be admitted to the physical memory, that is the RAM, and then on the availability of the CPU, whenever it is available, it will be allocated to the CPU. Okay, and it starts executing. During the execution, there are many scenarios. During the execution, particular, process may demand, particular process may demand for any data item, may demand for any IO device, may demand, or an unnecessary interrupt has awakened, or a time slice has expired. I'm coming to that time slice as well. As and when these things happen, the particular process in a multi-programming environment, of course, a particular process goes from one device to another device. Just for an example, we say that, I don't know whether this is there or not. No, it is right now, it is not there. Say for example, I'll go by making this a particular process. This is CPU. Okay. It is connected to some physical memory where I am having process P1, P2, P3. These processes are available in my physical memory. And then this is connected to a bigger memory, which my CPU cannot access. This is my secondary memory where I have constituted a job pool. Okay. Then, like this CPU, we have other devices. Say for example, disk. We have this subsystems or any other device, printer device. Are you getting what I'm telling? Are you understanding the scenario that I'm trying to explain?
Yes, sir.
Am I audible or not? Yes or no? Speak up.
Yes, sir. You're audible.
Okay. So you see, right now when I say that this process P0 is in the CPU, what is happening to this P1 and P2? This P1 and P2 are in a ready state, waiting to get the CPU, Right now, this P0 is executing, and all of a sudden it needs a disk movement. That is, it just wants some data to be transferred from disk to memory or memory to disk. What will it do? It will stop executing, go to the disk to do the I. Okay, to do the activity it requires. When it is coming to the disk, there can be two scenarios. Either the disk is available or the disk is already engaged in some activity. In that case, this process P0 needs to wait. It is something like when you are in the class, I'm teaching, all of a sudden a student says, "Sir, I'm thirsty, I need to go and have some water." So we can relate this to an IO activity. In a most jovial mood, I'll say, "Okay, go." So what it is doing, it was under execution, it just left the CPU. If we consider the class to be the CPU, it left the CPU, it went to the nearest aqua guard that is fitted, although I don't think our department have that facility anyway. There, if the terminal is free, that is no other person is filling up his bottles or anything, it will directly go and access the drinking water, drink it, and come back. In another scenario, you can understand that a few more students are there, those who are either drinking water or filling up their water bottles. What will these student who has left my class do? This student will have to wait. हेलो सर, मैं क्लास में हूँ, बाद में बात करता हूँ. Okay, understood this one? The thing that I'm trying to make?
Yes, sir. Yes, sir.
Yes, sir.
One strict warning to you guys. Please do not write this example in your copy. This is just to make you understand. It's a very non-technical example, but please do not write it in your copies in the examination. हाँ, समझ लो बात को. पता चला आप ऑपरेटिंग सिस्टम समझा रहे हैं पानी पीने के उससे. मैं सिर्फ आपको समझाने के लिए बोला. Okay, so that very concept goes like this here. For this disk or for any of this one, this will be waiting here. P1, P2, or any other processes which has just has been leaving the CPU for doing this. You see, these particular processes execution is not over. It requires some resources to be given, either in the form of a data or in the form of an IO devices or in the form of printer devices, peripheral devices, whatever. So while it is using these peripheral devices, it is not using this CPU. It is not using this CPU. Okay, so it is not exactly executing. So this particular time when it spends with the IO devices or it is spending in the ready queue, we say that the process is waiting. Only the time when it is with the CPU, we say that the particular process is under execution. Okay, is it clear? Now,
Yes, sir.
now coming to the notion of the question that has been raised by Arnab, that what happens if the RAM is full? Now, there are scenarios when the RAM is full. When a process has been created, say for example, I have P0, P1, P2, and right now a new process P3 has been created. Right now the process P3 has been created. Creating the process is easy. We can go on creating, but executing the process is a problem. Why? Executing the process is a problem. Why it is a problem? Because we have limited resources. We have limited resources. Even in the most efficient multiprogramming system, multiprogramming environment, we need these processes to get allocated to this particular physical memory. Now, as and when if memory is full, it has to wait. Wait where? Wait in the job pool. Wait in the job pool. This job pool is where? This job pool is anything, anywhere, but not in the physical memory. But not in the physical memory. Okay, but not in the physical memory. As and when one of these processes, P0, P1 or P2 terminates, or exits the system, this P3 will be given the chance to get allocated in the physical memory. There is a catch again. I'm saying P0 leaving the system somewhere, sometime, at some time. But now P3 is waiting in the job pool. We need to get this P3 in the place of P0. Then it also sees the memory requirement. Whether the memory which has been left by P0 is sufficient to admit this P3 or not. If it is not sufficient, then also P3 will not be getting admitted to the physical memory. It will wait in the job pool. Okay, it will be in the new state only. It will not become a ready state. Another scenario when Arnab has asked that what if my RAM gets filled? I don't know in what context you have asked, but are you listening, Arnab? Arnab?
Yes, sir.
Okay. See this one, stack, heap, data, this one. So the amount of memory that is being allocated to the process is fixed. Within this particular fixed memory, it has to do all this stuff. That is, stack बढ़ना भी पड़ेगा, घटना भी पड़ेगा, heap बढ़ना भी पड़ेगा, घटना भी पड़ेगा. That is the dynamic memory area that has been provided to the particular process. Now, I am having a scenario where my RAM is full. That is, all the slots I have given to the processes. अब एक process execute कर रहा है, उसका stack dynamically बढ़ रहा है, घट रहा है, बढ़ रहा है, घट रहा है. जब तक ये उस memory को cater कर पा रहा है, तब तक ठीक है. It's fine. It will get executed. But as and when the heap or the stack grows in such a manner that ये whole पूरा occupy कर लिया, उसके बाद भी बढ़ने की कोशिश कर रहा है. After that also it is trying to get more physical memory or more memory. In that scenario, that process will get terminated. This is an abnormal termination. This is an abnormal termination. This is called abort. This process will be aborted and sent back to the job. भाई तू चुपचाप वहां पे जाके बैठ जा. This process will be restarted when? कब restart होगा? तब restart होगा जब मेरे system के पास available physical memory होगा, so that it can cater the needs of these processes. I can cater the need of this process. Are you getting this point? Are you getting
Yes, sir.
this point? जब तक मैं need को cater कर पा रहा हूं, I can cater. But when you are demanding something which I don't have right now, what will I do? I'll just suspend you or I'll abort you. I'll just abort you, send back to the place where you have come from, and I'll ask you to wait there. जैसे मेरे पास वो memory available होगा, I'll ask come. Then we will restart the process. It may happen that a particular process may go on getting aborted in the want of this resource, which we call physical memory. Okay, this is a classical example of starvation, resource starved. एक particular process को मैं बार बार खत्म कर रहा हूँ क्योंकि जो resource it is demanding, it is not available with me. Arnab, is it clear now, or you want some more explanation?
Yes, sir. Yes, sir.
Okay. So this was the case. This is the case.
Sir?
Yes, please.
सर जब P0 वो CPU से निकल के डिस्क यूज करने जाएगा एग्जीक्यूट होके वो वेटिंग स्टेट में है ना, तब CPU क्या P1 को एग्जीक्यूट करना स्टार्ट कर देगा कि वेट करेगा?
देखो, in classical cases what happens is there are two types of programming environment. I was avoiding this discussion. Okay, I was really avoiding this discussion because it will come later on where I'll be more equipped with more information, or you will be having more information to decide on this one. One is a preemptive environment. Another one is a non-preemptive environment. Preemptive and non-preemptive environment क्या होता है? what happens in a preemptive environment, what happens in a non-preemptive environment. The example that, or the question that you have asked is about a preemptive environment. Okay, preemptive environment में क्या होता है, जैसे P0 आया, it has come to the CPU, बड़े मुश्किल से नहा धो के आए हैं, it gets executed. CPU भी अपने मजे से उसको एग्जीक्यूट कर रहा है, लेकिन P0 को जब भी लगा कि I need more resources in form of data or memory or IO devices, or I am waiting for an event to occur. The process P0 will on its own release the CPU. CPU को वो छोड़ देगा, CPU को फ्री रख कर देगा. In that case, CPU to P1 or P2 or P3 or any other process that is available according to the scheduling algorithm in the place. बात समझ में आई? बात
Yes,
समझ
sir.
में आई? मतलब with the permission of P0 only. P0 ने परमिट किया CPU की कि भाई जा, तू जी ले अपनी जिंदगी. But in a non-preemptive environment, once P0 has been allocated the CPU to process P0, P0 कुछ भी कर ले, CPU को नहीं छोड़ेगा. CPU को एंगेज ही रखेगा, जाके IO एक्टिविटी करेगा. CPU को एंगेज ही रखेगा, जाके प्रिंटिंग सर्विसेज देगा. CPU को एंगेज ही रखेगा, जाके डिस्क मूवमेंट्स करेगा. CPU को नहीं छोड़ेगा. In a non-preemptive environment, a CPU is allocated to the process from the very beginning to the very end. जब तक P0 उसको अपनी इच्छा से नहीं छोड़ेगा, तब तक CPU P0 को ही allocated रहेगा, no matter whatever it does. Either it is executing, or it is waiting for a device, or it is doing some disk movements, or it is doing some printing services. Doesn't matter. समझ में आ रहा है बात?
Yes, sir.
मैं इसीलिए ये इस चीज पे जाना नहीं चाह रहा था. Anyway,
Sir.
yes, please.
सर जैसा भी आप बताए, नॉन प्रिमिटिव एनवायरनमेंट में कोई प्रोसेस अगर सीपीयू पे एलोकेट हो जाता है,
प्रिमिटिव नहीं है, ये प्रिएम्प्टिव है.
हाँ प्रीएम्प्टिव, हाँ नॉन प्रीएम्प्टिव एनवायरनमेंट में जब कोई प्रोसेस सीपीयू पे मतलब एलोकेट हो जाता है तो उसको छोड़ता नहीं है. तो बहुत सारा वैसा सिस्टम होता है ना, मतलब ज्यादातर सिस्टम जो एक साथ मल्टीटास्किंग करता है तो वो इस तरह से करता है कि एक ही प्रोसेस को ये कुछ समय पे काम करता है, फिर छोड़ के दूसरा प्रोसेस पे काम करता है. तो नॉन प्रीएम्प्टिव एनवायरनमेंट में तो मल्टीटास्किंग नहीं हो पाता होगा.
Non-preemptive environment, multitasking, multi-programming environment are associated with your RAM. You see, this is not related to multitasking or this one. This is related to the memory management policy that you have implemented. First of all, multi-programming environment किस लिए आया और क्यों आया? You have to understand this. Or when we say that it was a uni-programming environment, why it was called a uni-programming environment? When we started our computing journey or this operating system's journey, these devices were very new. That CPU, physical memory, memory cycles, these were very, very new. So अगर आपका एक CPU है, we understand that CPU can execute only those processes which are in my physical memory, right? इतना तो
Yes,
पता है.
Yes, sir.
पहले जब memory management unit was in its very primitive stage, memory में कुछ भी कर लीजिए, सिर्फ एक प्रोसेस ही रहता था. कुछ भी कर लीजिए, सिर्फ एक प्रोसेस ही रहता था. यानी मैं एक पूरे मेमोरी चंक को एक पूरे रैम को मैं एक पर्टिकुलर प्रोसेस को एलोकेट करूंगा, मैं रैम को तोड़ मड़ोड़ नहीं सकता था. I wasn't able to segment this RAM. so that I create different segments where different processes may reside. So this was uniprocessing system, programming environment. फिर भाई किसी लोगों ने बोला नहीं अच्छा रैम तो बहुत बड़ा है, प्रोसेस तो छोटे छोटे आते हैं, एक एक प्रोसेस को इतना बड़ा बंगला देके कोई फायदा नहीं है, हम क्या करेंगे, हम क्वार्टर साइट्स बनाएंगे, पूरे पूरे लैंड को लेंगे और फ्लैट्स बना देंगे, ठीक है, दैट इज वी विल सेगमेंट. हमने जब सेगमेंट शुरू किया तो हमने क्या किया, more number of processes we could allocate according to the size of the segments that we have created, also the demand, memory demand of the process, keeping in view of the memory demand of the process. So what has happened, my RAM can hold multiple processes, my RAM can hold multiple processes. अब एक प्रोसेस आया, उसने एग्जीक्यूट किया, जब उसको जरूरत पड़ी इधर उधर जाने की तो उसने सीपीयू को बोला भाई रुक मैं जाके आता हूं. इट इज ऑल्सो मल्टीटास्किंग, इट इज ऑल्सो मल्टी प्रोग्रामिंग एनवायरनमेंट, क्योंकि मेरे फिजिकल मेमोरी में मोर देन वन प्रोसेस, मोर देन wherever my physical memory is allowing more than one process to get admitted, we say this is a multi programming environment. And there are situations where we do not want preemption to happen. We do not want preemption to happen, such as critical section problem. आप कोई एक shared memory को बहुत ही critically आप update या कुछ कर रहे हैं, उस environment में मुझे नहीं चाहिए कि कोई आके मेरे प्रोसेस को इंटरप्ट करे, ठीक है. I don't want any other process to come and interrupt it because it's a critical job. So when we आया मेरा प्रोसेस सीपीयू में आया, प्रोसेस को बोला भाई रुक मैं आ रहा हूं, सीपीयू वाज वेटिंग. अब वहां जाके इफ इट गेट्स टर्मिनेटेड फॉर सम रीजन, फॉर एनी लॉजिक एरर और एनीथिंग, मेरे प्रोसेस अवेलेबल है, कोई प्रॉब्लम नहीं है. लेकिन इफ इट जस्ट कम्स बैक देन इट जस्ट एग्जीक्यूट्स इट एंड देन kicks it up. But when we have gone to that particular stage where CPU is waiting for that process to come back from IO, the system statistics says that we have not utilized the devices very efficiently. I'm wasting the time of CPU. Then we said no, there will be a preemptive environment. There will be a preemptive environment where whenever a process goes to any other device, either it is waiting or doing anything, it must release the CPU. From then we have come to this one. Going to that, it releases the CPU. CPU is free to get allocated to any of the process according to the scheduling algorithm. भाई P0 है, P1 है, P2 है, क्यों भाई P0 को ही पहले दिया जाए, P3 को क्यों नहीं दिया जाए, P1 को पहले क्यों नहीं दिया जाए. तो ये शेड्यूलिंग एक स्ट्रेटेजी है, जिस शेड्यूलिंग स्ट्रेटेजी के हिसाब से हम लोग सीपीयू को एलोकेट करते हैं, ठीक है.
तो मतलब अगर वो मल्टीटास्किंग में अगर प्रोसेसर अलग अलग प्रोसेसर्स के बीच में जंप करता है तो वो उसको डीएलोकेट नहीं कर रहा होता है.
किसको डीएलोकेट नहीं करता है? अगर प्रोसेस को अगर सीपीयू से डीएलोकेट ना किया जाए तो सीपीयू जंप नहीं कर पाएगा, क्योंकि जैसे सीपीयू को एलोकेट किया जाता है, सीपीयू क्या है, व्हाट इज द सीपीयू. इनके जितने जनरल पर्पस रजिस्टर्स है, इनके जितने स्पेशल पर्पस रजिस्टर्स है, इनका जो एएलयू है, अरिथमेटिक लॉजिक यूनिट, ये सब मिला के तो सीपीयू बनता है ना. अगर आपने इस प्रोसेस को डीएलोकेट नहीं किया तो एक जन का जो डाटा रजिस्टर्स में है वो दूसरे जन के साथ मिल नहीं जाएगा. बात समझ में आई मैं क्या बोल रहा हूं? हेलो, हेलो, am I audible to you all?
Yes, sir. Yes.
बात समझ में आई क्या बोल रहा हूं मैं? जब सीपीयू को एक प्रोसेस से लेके दूसरे प्रोसेस में दिया जाता है, ऑफ कोर्स उस प्रोसेस को डीएलोकेट किया जाता है सीपीयू के साथ। अगर उस प्रोसेस को सीपीयू से डीएलोकेट नहीं करेंगे, सीपीयू क्या है? आपने अगर आर्किटेक्चर पढ़ा होगा, सीपीयू क्या है? Special purpose registers, a group of special purpose registers are there, a group of general purpose registers are there, data registers are there, program counters are there, and then your ALU logic is there, arithmetic logic unit is there. Yes, अगर मैंने इस प्रोसेस को सीपीयू से डीएलोकेट नहीं किया, मतलब प्रोग्राम काउंटर में किसका इंस्ट्रक्शन रहेगा? जो प्रोसेस वेटिंग में है उसका रहेगा, या जो अभी नया मैंने एलोकेट किया है इसका रहेगा?
जो वेटिंग में है उसका।
That's why we need to deallocate the CPU from the current process. Okay, this deallocation is called preemption. CPU has been preempted. ठीक है? We'll go ahead. It will be clear when we go ahead. It's just starting, beginning. Beginning has journey. Anyway. So every process have one structure. This is called a process control block. What is this process control block? The information associated with each process. जब हम एक चीज को प्रोसेस बोलते हैं, प्रोग्राम को, टर्मिनोलॉजी, then we call it a process control block. तब इसी चीज को हम टास्क बोलेंगे, इसको बोलेंगे टास्क कंट्रोल ब्लॉक. When we call it a job, we will call it a job control block, and so on. So these terminologies are actually used interchangeably. Doesn't matter. Let's see. I have process state, that is one of these states that we have done. Either it is running or ready or waiting. Okay. Then we have program counter. That is the location of the instruction to the next. Location of the instruction to execute next. Okay. Then we have CPU registers, that is contents of all process centric registers. General purpose register ho, address registers so, instruction registers so, instruction set so, sare ke sare values. Then we have CPU scheduling information. What type of scheduling in algorithm that we are using? Either it is FCFS, or it is SJF, or it is round robin, or it is multi-level feedback queuing, or it is feedback queuing, whatever it is. Or it is a priority scheduling, whatever it is. Okay. So associated with this are what are the priorities of the process, what are the values of the queue pointers and all. This will be kept by this particular flag information. Then we have memory management information. Memory allocated to the process. How much memory is allocated? What is the maximum memory that it can be allocated? Okay, that it can be allocated, and this accounting information, that is how much CPU is used. What is the time that has elapsed from start time, and how much time it can be allocated. Okay, these things are accounting. Then IO status information, that is the devices allocated to the process, list of open files and all. These things will be there, and many more, and many more. So all these constitute a process control block. This block will contain the information or the essence particular process. Okay, so how, when we talk about this thing, how this processes go on switching from IO devices to the process, to the CPU and this and that. So we have these two processes, just diagrammatically we are, as right now, we will see. We have these processes P0 and P1. So in the very beginning, we say that this P0 is executing, and all of a sudden this interrupt has come. Whatever we are studying, the OS is interrupt driven. If I disable the interrupts, the system clock will also not work. So even the clock is updated using an interrupt mechanism. So whatever we need to tell to the CPU, this is being told in terms of interrupts. Okay, interrupts are, we can say it is a system call. So it is executing right now, and some interrupt or a such system call has come. This system call will let the operating system to save the state of this particular process P0, that is save state into PCB. जो भी करंट इंफॉर्मेशन है, स्टैक इंफॉर्मेशन से लेके, हीप इंफॉर्मेशन से लेके, प्रोग्राम काउंटर से लेके, जनरल पर्पस रजिस्टर्स से लेके, शेड्यूलिंग एल्गोरिथम्स से लेके, सब कुछ we will just store in the PCB. Okay. Right now, when we say this P0 was there, it was not executing anything. It was idling. All of a sudden, a system call has come. This led the PCB of P1 to get reallocated to the CPU. And once it has reallocated, it starts executing. Again, any interrupt or system call will lead this PCB1 to get saved. That is, leaving the CPU, and this goes on, and ultimately when this starts executing, this also will execute when? This will execute when we have an interrupt call. So it gets loaded, starts executing. For every start of execution, we will reload the PCB into my CPU. So we can say that whenever we are looking into this broader structure or broader scenario, process do alternate between an executing and in the idle phase. Now this idle phase, what exactly the process is doing? A process may be waiting for an event, कि मैंने एक प्रोग्राम लिखा, ये कुछ एग्जीक्यूट करके अपने आप को ब्लॉक कर लेगा. कब तक ब्लॉक करेगा? जब तक से फॉर एग्जांपल 15th of September ना आए. The date movement of this 15th of September is an event. It is waiting. ये जब तक ये event नहीं आएगा तब तक ये execute करना शुरू नहीं करेगा. What exactly this particular process is doing? This particular process is waiting for that event to come. It is not finished, but it is just waiting for the event to come. Similarly, a particular process in this idle time means what? Idle time of the CPU, not the process. In this idle time, it may be waiting in another queue. For another device to get allocated to this particular process. Okay. Likewise, this particular process is either idle, that is waiting for an event, waiting for an IO device, waiting for something, waiting for an interrupt to get over, and so on. And then it is executing. Once it has been done, it is executing, and then again it is going to get idle. So this is a timeline analysis of two processes, how they alternate between idling state and executing or running state. Are we clear about this thing? Any confusion in this one? Anyone? Sunil, are you there?
Yes, sir.
समझ में आया?
Yes, sir.
Very good. So we go ahead. We will not see threads right now. We will come to threads later on. Now, A process representation in Linux, we can see I have PID. It's a process identifier. PID itself is a data type. It's a data type. Then we have state, long state of the process. Time slice is there. Scheduling information. Then these are processes. I have task structure, parent. This is the process's parent. We have children. This is the children of this particular parent. We have files. That is list of open files that is actually needed for that particular this one, and address space of this process. This is how a particular process is getting represented in my Linux system. Windows system is much more complicated than this one. Okay. Now, process scheduling. Why do we use process scheduling? Why do we use process scheduling? I don't think here it is there or not. Yes, queuing diagram is there, scheduler, long-term scheduler. Okay. We will finish off this. Maximize CPU use. Quickly switch processes onto CPU for time sharing. We have process scheduler, selects among available processes for the next execution on the CPU. Scheduling queues of processes, that is job queue, ready queue, device queue, and all. What is a job queue? Set of all processes in the system. You see the diagram that we have made. This is job pool. All the processes which is here in this area, job pool, we say that those are in job queue. Okay, those are in job queue. Then we have ready queue. What is ready queue? What is
The
ready?
processes that are ready to get executed
Yes,
are restored in ready queue.
Yes, ready queue are the processes which have been admitted in the physical memory and ready to get executed. These are all a ready queue. Okay. Where is job queue? Job queue is in my secondary memory device. Where is ready queue?
Sir,
Primary memory.
RAM.
Exactly. RAM, physical memory, or primary memory. Then we have device queue. Set of processes waiting for an IO device. Where is it?
sir, same in the RAM.
In the RAM itself.
In the
Now,
RAM, yes, sir.
Now you see the process migrates among the various queues. Okay, the process migrates in my various queues. Remember that process is in physical memory. That does not mean that it is ready. It have to be in the physical memory and in a specialized area, which is called a ready queue. Then only we say that the process is ready to get executed. It might be in a RAM, it might be in a physical memory, but it is waiting in a device queue. So we cannot say that the process is in a ready state. The process is in not in ready state. The process is in waiting state. Rather we say process is in waiting state. Why? Because it is in a device queue waiting for that particular device to get allocated so that it can do its job, whatever it is required with that particular device. So here is a pictorial diagram. I have this ready queue. We have PCB7, PCB2. These are shorted, head and tail. We have this linked list, doubly linked list. Okay, not doubly linked list. This is a linked list only. Another linked list only. So then we have magnetic tape unit 0, no processes waiting here. We have magnetic tape 1, no processes waiting here. We have disk unit 0. We have 3 processes waiting here. We have terminal unit 0. We have 1 process waiting here. Now these are the examples of different queues that are available. Once, say for example, process PCB7 means process P0 has asked for this magnetic tape. What will happen? This will remove itself from the ready queue. And go and attach itself into this particular magnetic tape unit 0. In the ready queue also it was waiting. It was waiting for a device. Which device? CPU. And in other devices, it is waiting for any other device, that particular magnetic tapes or disk drives or terminal drives or anything. Okay. So this is the representation of a process scheduling, that is queuing diagram. We say that my process enters through the ready queue. अगर बहुत lucky रहा, if it is a very lucky process, it will get allocated to the CPU. In 1 or 2 CPU cycles only, it will get over and leave the system. Must happy. But if it does not, what will happen? From CPU, it will go to the IO request. That is IO request to the IO queue. Okay? जहाँ पे IO हुआ, वहाँ पे IO करके, what will happen? It will just go on, attach itself with the end of the ready queue. End of the ready queue. Or it might happen that हम लोगों ने हर प्रोसेस को, से फॉर एग्जाम्पल जैसे हमारा टाइम टेबल बना है, आज के क्लास के बाद तो मेरा टॉपिक खत्म नहीं हो जाएगा, मुझे नेक्स्ट क्लास का इंतजार रहेगा अकॉर्डिंग टू टाइम टेबल. यानी मेरा 1 घंटे का क्लास जब खत्म होता है, व्हाट विल आई डू? आई विल जस्ट लीव यू गाइस. सिमिलरली वैसे ही एक प्रोसेस को एक टाइम दिया जाता है, दिस इज कॉल्ड अ टाइम स्लाइस. हर किसी में नहीं होता है. व्हेन वी आर टॉकिंग अबाउट राउंड रॉबिन शेड्यूलिंग, वी विल प्रोवाइड अ टाइम स्लाइस. Every process has to execute up to that time slice. Once that time slice has expired, it will leave the system. It will leave the CPU and attach itself to the end of the ready queue. This is what is happening. जैसे ही बाकी सब लोगों को उतना टाइम मिल जाएगा, फिर से ये अपने आप को प्रेजेंट कर देगा सीपीयू के लिए एग्जीक्यूट करने के लिए. ठीक है, दिस इज कॉल्ड टाइम स्लाइस एक्सपायर. और इट इज डूइंग अ फोर्क. व्हाट इज अ फोर्क? फोर्क इज अ system function. Using this fork function, we create child. So when we go for a fork, what happens is the process, which is called a child process, this particular process loads its memory or its program into the child and it goes on sleeping. उसका बच्चा जाएगा, that child process will go एग्जीक्यूट करके काम वाम करके रिजल्ट पेरेंट प्रोसेस को देगा. पेरेंट प्रोसेस यूजर को वो पर्टिकुलर चीज देगा और फिर टर्मिनेट होगा. वी विल नॉट टॉक अबाउट दिस, बट वी से दैट फोर्क अ चाइल्ड. फोर्क को बहुत अच्छे से मैं कराऊंगा. और इट इज वेटिंग फॉर एन इंटरप्ट. So these things are the queuing diagram of a process scheduling. A particular process will have to go through these particular queues in its lifetime. Okay, it might not go, but in general it goes through these things. Now we have schedulers. What are schedulers? In principle or in practice, we have only 2 types of scheduler. Another scheduler has been added later on. We will talk about that. What are these schedulers? We have a short-term scheduler. We have a long-term scheduler. What is a short-term scheduler? Short-term scheduler is the scheduler which selects a process from the ready queue and allocates it to the CPU. That is, selects which process should be executed next and allocates CPU. That is, from the ready queue, it picks up a process from the ready queue and it allocates the CPU to that particular process. This is called a short-term scheduler. You see, short-term schedulers are invoked very infrequently. कब होगा? Say for example, एक पर्टिकुलर प्रोसेस आपका सीपीयू में है, रेडी क्यू से सीपीयू में आया, सीपीयू से तुरंत ये आईओ रिक्वेस्ट के लिए चला गया. सीपीयू क्या है? खाली बैठा है. अब क्या करें? अगर ये शॉर्ट टर्म शेड्यूलर दूसरे प्रोसेस को शेड्यूल ना करे तो सीपीयू बैठा रहेगा. So it will just invoke the short-term scheduler so that a particular process may get allocated to the CPU. That's why we say that a short-term scheduler gets invoked very frequently. कुछ भी हुआ, IO request हुआ, time slice expire हुआ, terminate हुआ एक process, या फिर एक interrupt आया, CPU needs another process to get for its working to go on. So short-term scheduler will be invoked. Another one is a long-term scheduler. What is a long-term scheduler? A long-term scheduler is the scheduler which brings processes from the job pool to the ready queue. From the job pool to the ready queue. This is not very frequent one, because when we are scheduling these processes from job queue to ready queue, we are not scheduling one. What we do, we bring in batches. 3-4 प्रोसेसर्स को एक बार में डाल दीजिए आपके फिजिकल मेमोरी में. अब जब तक वो फिजिकल मेमोरी खाली ना हो या रेडी क्यू खाली ना हो या जगह बचे ना, तब तक आप दूसरे प्रोसेसर्स को नहीं ला सकते. So what is the difference between this short-term scheduling and a long-term scheduling? Short-term scheduling works from ready queue to the CPU, whereas long-term scheduling works from the job pool to the ready queue. Okay, short-term scheduler is invoked very frequently, whereas long-term scheduler are not that frequently. Infrequent invocations are there. Now, coming to this particular notion, we have a type of processes. We have this type of processes. We have IO bound processes and we have CPU bound processes. अब तक तो सिर्फ processes पढ़े थे. अभी differentiation, processes के differentiation. What is this difference? We have IO bound or we have CPU bound. What do you mean by an IO bound process? An IO bound process spends much of its time. Say for example, अगर 100% time को हम लें, 80 to 85% time it spends with the IO devices only. Okay. And what about a CPU bound processes? CPU bound processes, the process which spends most of its time with the CPU devices. Okay, so we have these two different types of processes. One is an IO bound process, another one is a CPU bound process. Now, from this one, একটু বসাবো আমার 2 মিনিটের ক্লাস আছে, একটু বসাবো ক্লাসে আছে আমি আইতেছি. So we have two types of processes, CPU bound and IO bound. Now, what do you think? What type of processes do we want in my system? IO bound processes or CPU bound processes? And please speak up.
Sir, CPU bound processors.
Okay. Any more answers? Sohan Sagar Sinha has left the meeting. Has joined back. Yeah, please tell. Raj has told to be CPU bound process. And Raj, why do you want only CPU bound processes? Raj,
Yes, sir.
why do you want only CPU bound processes?
Sir, I don't know exactly. I read in the PDF, sir.
You
Sir,
read in the PDF.
yes, sir. Sir, that it is predictable to hold longer scheduler will allow
Acha,
like that. Sir.
okay.
Don't know
What
exactly.
about this
Right.
Uddeshya Raj? What do you think? Are you listening?
Sir,
Or you have... हाँ?
सर मेरे ख्याल से दोनों ही जरूरत पड़ेगा. बिना इनपुट आउटपुट के कंप्यूटर ऑपरेट कैसे करेंगे?
नहीं, ऐसा बात मत सोचिए कि CPU बाउंड प्रोसेसर सिर्फ CPU में बैठा रहेगा, इनपुट आउटपुट नहीं करेगा. मतलब मैं कह रहा हूं दो बच्चे हैं, उसमें मैं डिफरेंशिएट कर रहा हूँ, एक पढ़ाकू बच्चा है, एक खेल कूदने वाला बच्चा है। ऐसा तो नहीं हो सकता कि पढ़ाकू बच्चा खेलता ही नहीं है और खेल कूदने वाला बच्चा बिल्कुल पढ़ता नहीं है, ऐसा तो नहीं है। दैट इज a CPU bound process will have IO, will do IO, input output, it will also have to do, but not much. That is 15% of its entire time that it spends in the system will be dedicated to IO devices, and 85% of its time will be in the CPU. Whereas a IO bound process, similarly 85% of its time will be spent with the IO devices, and 15% of its time, the entire time, will be spent with the CPU. So my question, very clear question, and even the book has asked, what do we want in my system, IO bound processors or a CPU bound processors?
Sir, both.
मेरे ख्याल से सर CPU बाउंड ज्यादा सही रहेगा, क्योंकि IO डिवाइसेस जनरली CPU डिवाइसेस से स्लो होता है।
अच्छा, Tamalika, you were telling something.
Sir, I was telling that both should be there. Like CPU bound processors should also be there, and IO bound processors should also be there, so that whenever an IO bound process is working on IO, as an IO bound process mostly spends in time in doing IO operations. So whenever it will go to do the IO operations, I can execute the CPU bound processes. So, yes, sir.
Yeah,
Both
that's
should
the correct answer. We need a very good mix. Why we need a very good mix? You see, if we have only CPU bound processors, my IO devices will be underutilized. पैसा देके खरीदा है भैया, ऐसे थोड़ी बिठा देंगे, काम कराएंगे ना। So we want optimal device use. मेरे सिस्टम का कोई भी ऐसा डिवाइस नहीं होना चाहिए जो खाली बैठा हो। That must have some work to do. That is called optimal resource utilization. Okay, so if we have only CPU bound processors, my CPU will be overworked while my IO devices will be sitting idle doing nothing. At the same time, if we have my IO bound processors, my CPU will be doing nothing. It will be minimal work it will do, and it will just go on having a very good time. We don't want that. We want a very good mixture, so that none of my devices